Hello students, welcome to lecture 12 of the online course on Nanophotonics, Plasmonics and Metamaterials. Today we will be covering real and reciprocal lattices. So here is the lecture outline. So today we will have a look at the periodic electromagnetic devices, like why we are studying these topics and where is the final objective. We will also go into the technical details like two-dimensional lattices, study about their symmetry operations. We will also understand the translational symmetry that is present in these periodic devices. We will analyze the primitive lattice vectors, calculate the reciprocal lattice vectors, obtain Miller indices and also discuss about the Brillouin zones. So here is the final objective. So as you can see, we actually use a lot of periodic electromagnetic devices in our different applications, starting from diffraction grating. You might have heard of this diffraction gratings that allow you to split light into different colors. So you can use it for spectral imaging. You can use photonic crystals as waveguides for guiding light. You can also have photonic crystal based fibers, hollow core fibers. Okay. Then you can actually make band gap materials with a defect at the center, which will allow you to this will act as a resonator cavity. These periodic structures can also form metamaterials, as we have discussed initially, that you can actually engineer the electromagnetic properties of material using this kind of periodic arrangements. Obviously you can make antennas, okay, and slow wave devices. You can also make frequency selective surfaces that are also useful for, say, stealth application. So you can understand that starting from optical benches to data communication on chip, data communication over cables, resonator cavity, metamaterials, antennas, frequency selective surfaces, all this application have they use periodic electromagnetic structures. So that is why it is very important to understand the structures in little bit of details, and that is the reason why we are discussing this photonic crystal. That is the first example of the periodic devices we are dealing in this course in little bit of depth. So let us first go and ask the question that what is a periodic structure. So if you look into periodicity, that is present at the atomic scale. So all these atoms, they actually have a periodic lattice in which the electrons or the elements are oriented, or their positions. So different atoms, they are all positioned in different lattice points. And if you copy that natural thing into your engineered object, you can also make periodic arrangement of different structures which are periodic in 2 dimension or 3 dimension depending on your application need. So here also you have large scale periodicity. Here we have discussed about atomic scale periodicity. Now because it is periodicity, the math describing these things in both this atomic scale and large scale, they are basically same. Now how do you describe periodic structures? There is an infinite number of ways that the structures can be periodic. Despite this, we need to find a way to describe and classify periodic lattices. So we have to make generalization to do this. So what are the generalization? So let us see that we can classify periodic structures into 230 space groups, which can be classified into say 32 crystal groups, or you can say they can be classified into 14 Bravais lattices. I believe from the material science kind of courses, you might have heard about the 14 Bravais lattices that is present, and they also fall under 7 crystal systems. So these are kind of generalization. So as you see, so this is, as you go down, they become less specific and they are becoming more generalized. Now, what are these space groups? These are set of all possible combinations of symmetry operations that restore the crystal to itself. Okay, so what are the different possible combinations of operation you can perform on a particular crystal? Now, if you take the example of the 14 Bravais lattice, they basically are the primitive lattices. That means these are set of all possible ways a lattice can be periodic if composed of identical spheres placed at the lattice points. So, these are like lattices are the structure at which you can repeat the unit cell. So, here if you take identical spheres as your unit cell, that you can place at every lattice point, and that will create that particular arrangement. Okay. So, when you talk about crystal systems are basically set of all Bravais lattices that have the same holohedry, that means the shape of the conventional unit cell. So, if you actually look into the classification based on crystal systems, there are only 7 crystal systems. Okay. So, here they are basically the set of all Bravais lattices which have the same shape of the conventional unit cell. Let us look into some of these examples. So, if you take 2D Bravais lattices, so here you see this is one lattice. So, you look at the arrangement here, this is basically hexagonal. So, you see the green shaded region that shows a hexagonal shape. So, at each of this point, what is sitting there? It is a sphere or an atom or any other shape can actually sit here, okay, to make this particular lattice. So, what are the important things? You have to see that here the two lattice vectors, they are equal in size and the angle between them is 120 degree. So, that is hexagonal lattice. You can also have square lattice. So, here the two lattice vectors are equal in size and the angle between them is 90 degree. Make sense? In rectangular, you have to understand that the two lattice vectors are no longer equal. Okay? So, this will be longer and this will be shorter, but the angle between them has to be 90 degree. There can be other shape like rhombic or centered rectangular like this. It is a rectangle with one at the center. So, in that case, this is how now the two lattice vectors are related, and here also the angle requirement is not 90 degree. You can also have oblique like this, where modulus of T1 is not equal to T2. That means the two lattice vectors are not equal to each other and their angle is also not 90 degree. So, these are like two dimensional Bravais lattices. When we talk about symmetry operations, these are the symmetry operations we discuss. So, one is called pure translation, it means moving. So, if you move these to this point, okay, the lattice orientation remains same. So, this is translation symmetry. Then you have rotation symmetry. So, if you take this one and rotate it like this, okay, you see upon this kind of rotation, it again gets back to the same shape. So, this is called rotation symmetry. Then you take this one, this is called reflection symmetry. So, if you take this part and take reflection of it, you will see you will get up the same kind of shape. So, this is rotation symmetry, and you can also try any combination of this translation, rotation and reflection. Sorry, this is called reflection symmetry. So, you can have any combination of translation, rotation and reflection, and that combination also give you a identical kind of transformation. So, these are called symmetry operations. Now, with that, let us try to understand the primitive and non-primitive lattice vectors in more details. So, as we understood that the axis vector define the shape and the orientation of the unit cell. They cannot uniquely describe all 14 Bravais lattices, but they could uniquely describe the 7 crystal system. Okay. So, the translational vectors, they connect adjacent points in the lattice and can uniquely describe the 14 Bravais lattices. So these are the two important things. One is excess vectors, which are good for 7 crystal systems but not good for the Bravais lattices, whereas the translational vectors are good for the Bravais lattices. Okay. Now the primitive lattice vectors are nothing but the smallest possible vectors that can describe the unit cell. We will take this as an example. So if you take this as your unit cell, as you can see, this is basically a BCC structure, body centered cubic structured. Okay, and here you can see that you have taken these are the 3 vectors. So you can say these are the primitive axis vectors. Whereas if you try to take the center point, from the center point if you are trying to connect the vectors to the adjacent 3 points, that is the primitive translational vector. Okay. So these are 2 different types of orientation, okay, or you can say nomenclature or systems. So one is axis vector, this way they are defined, another is translational vector, this is how they are defined. So almost always the level lattice vectors refer to translational vectors. So when we say lattice vectors, we basically mean these vectors which are able to uniquely describe the fault in Bravais lattices. So always remember, like lattice vectors, you have to uniquely describe the lattices, that is why we go for translational vectors. Okay. Now this one, this is a primitive translational vector, this one and this one. How about this? This is also a vector which is, you know, integral multiple of that particular primitive vector, and then you have one along this side. So what about this one? Is this vector a primitive one? No, it is not a primitive one. Okay, the primitive ones are the smallest possible vectors. So these are the smallest possible vectors, not this one. Okay, so this is the primitive translational vector, as you can see here, but this one is not the primitive one. So it's a non-primitive translational vector. Now let's look into the translational symmetry. So continuous translational symmetry can be observed, okay, in such a system where it is unchanged if we translate everything through the same distance in a certain direction. Like if you go back here and you see that if you shift the entire system, okay, then it is actually the system is unchanged. So that kind of symmetry is called translation symmetry. Okay. So given this information, we can determine the functional form of the system's modes. Now a system with traditional or translational symmetry is unchanged by a translation through a displacement d. So where we are quantifying the thing here. Now for each d we can define a translational vector td cap, okay, which on operating on a function fr. So if you operate this td cap, the translation on a function fr, it will shift the argument by the distance d. And what do we want? We want, you know, after the translation it should be same as the original system. Now a system with continuous translational symmetry in the z direction is basically invariant under all the TDS that can have in the particular direction. Okay. So continuous translational symmetry means if a system for any value of d is able to repeat itself, that is like a continuous translational symmetry system. Now what sort of function is an eigenvalue of all these TDs? Okay. We can prove that a mode with the functional form e to the power I k z is the eigenfunction of any translational operator in z direction. How it works? It works like this. So if you take this translation operator, okay, at any translation for any distance, say d, that works on this one, so that will actually shift the argument by d. So how it shifts? E to the power I k z minus d. So that can be written as e to the power minus I k d times e to the power I k z. So this becomes a eigenvalue equation, okay, and this is the eigenfunction, right? This is the eigenvalue, this is the eigenfunction. Okay, so the eigenvalue is e to the power minus ik t. So this is happening for any kind of translation, continuous translation. Now what about we have discrete translational symmetry? It means you cannot repeat at any arbitrary distance, but at a defined distance, if you repeat the system, you will see the same property. That is what is called discrete translational symmetry. Now photonic crystals, which are man-made crystals, okay, like traditional crystals of atoms or molecules, they do not have continuous translational symmetry. Rather, photonic crystals will exhibit discrete translational symmetry. That means they are not invariant under translation of any distance, but they will work for a given distance and its integral multiple. Okay. So you can actually take this particular example, as you can see that it is a 1D for periodic crystal or photonic crystal, where it is periodic along the y axis. Okay. So what is the period here? It is shown in this box. So this particular is the unit cell that is being repeated, and the repetition is happening at a distance of a. Okay. So at any sample point at a or integral multiple of a in plus and minus direction, you will have the same property. So these are basically systems with discrete translational symmetry, right? Now for this system we still have continuous translational symmetry is there, but that is along the x. So here it is continuous. Okay, along x direction the system is having continuous translational symmetry, but along y direction it is having discrete translational symmetry. So the basic step length is the lattice constant A, and the basic step vector is called the primitive lattice vector. In this case, what is the primitive lattice vector? It will be bold A, that is nothing but A y cap. It means it is along the y direction and the magnitude is A. Okay, that is how you can actually define the primitive lattice vector. Now why only one vector? Because this is 1D periodic. You are not bothered about what is happening in the other two dimensions. So periodicity is only seen in y. Now for this system, yeah. So in this case, what you can write, that along y it is periodic, along x it is also, it is having continuous translational symmetry, along y it is having discrete translational symmetry. What is happening along z axis? Along z axis you will see that the permittivity is a function of the distance, because it is changing with the coordinate z. So here it is, say the material is there, when you go up you may have the material or may not have the material. So it is basically changing. Okay. And along y, so what is happening? The dielectric function, you can say it continuously varies in the z direction. So here you will see a continuous variation. Okay. However, along y you will see that it is varying discretely, like epsilon r can be written as epsilon r plus minus a. So whatever you are seeing at position r can also be seen at position r plus a or r minus a. Now by repeating this translation, okay, you can see that epsilon r can be written as epsilon small r plus capital R. So what is capital R? It will be nothing but any integral multiple of the lattice period, which is small a. So r can be written as LA, L is the integer. These are very simple things. Okay. Now the dielectric unit that we have considered, we consider to be repeated over and over, just like this box is being repeated. Okay. Now what is this box called? In good terms it is called unit cells. Okay, because this is the thing that is being repeated periodically. Now in this example, the unit cell is an XZ slab of dielectric material which has got a width a in the y direction. So, if you describe your unit cell like this, it is clear that it is a 1D periodic structure. Now, because of the translational symmetries, eigenfunctions must commute with all of the translation operation in the x direction, as well as the translation operators for lattice vectors, that is r equals LAY in the y direction. So, with this knowledge, we can identify the modes of simultaneous eigenfunctions of both translational operators. So, there are two types of operator as I mentioned. So, you have this TDX e to the power I kxx, that is along x, it is a continuous translational symmetry. So, this will be the eigenvalue operation, okay, and along y you have this discrete translational symmetry, and that happens along r, that is LA, integral multiple of the lattice period. So, these are the two translation operation that is happening, and using this you can identify the modes of simultaneous eigenfunctions. Okay. Now, let us see how do you calculate the reciprocal lattice vectors. Now, we can begin to classify the modes by specifying kx and ky. Okay. So, kx and ky, they are in the momentum space, right. Now, however, not all values of ky will yield different eigenvalues. Consider two modes, one with wave vector ky and another with wave vector ky plus 2 pi by a. Okay. Now, what is this 2 pi by a? A is the lattice constant. So, you can have wave vector with these two values. Now, if you insert these values into the equations that you have seen here, these two equations, okay, they will show that they have the same T r cap eigenvalues. Okay. In fact, all of the modes with the wave vectors of the form ky plus m 2 pi by a, m is an integer, they will form a degenerate set, and they all will have the same T r cap eigenvalue of e to the power minus I ky LA. Okay. So, it means all these cases they will actually have the same eigenvalues. Now, this was done for say ky, right. So, augmenting ky by an integral multiple of b. So, if you define 2 pi by a as b, okay, so this is nothing but integral multiple of b. Okay. So, you understand that this will leave the state unchanged. So, you can actually call b equals b y cap as the primitive reciprocal lattice vector, right. So, real lattice and reciprocal lattice is in the momentum space, and there you can understand that whatever is you are adding integral multiple of that thing that repeats, so that will give you the reciprocal lattice vector. Now, suppose we have a function fr that is periodic on a lattice. So, periodic means you can write that f of r will be same as f of small r plus capital R for all the vectors capital R that translate the lattice into itself. So, it is repeating after this particular value of capital R. So, we have seen what is capital R, that is basically small l a, L is integer, A is the lattice constant, right. Now, our dielectric function epsilon r can also be taken as this kind of function. So, instead of f was a generic one, you can think of a property, material property like permittivity, that will also repeat using this particular relationship, and in this case capital R is called the lattice vector. Okay. Now, if you consider a two-dimensional arrangement, okay, so let us consider this particular picture, which is a periodic structure of identical parallel rods or tubes or veins. Veins will be like meshes, okay, like grids like this. Okay. So, you can assume these veins to be embedded in a homogeneous host medium and they are organized at the points of a rectangular lattice. So, what is happening here, you can think of a square or rectangular lattice. Rectangular lattice, as I mentioned before, that one lattice vector is not equal to the other lattice vector, that is rectangular lattice, but you have to make sure the angle is 90 degree. Now, in this case the impermeability, which is eta xy, can be written as epsilon naught over epsilon xy. Now, this is also periodic in the transverse directions, that is x and y. However, it is uniform along the z direction, because there is no change in the z direction, it can be infinitely large, the z direction. Okay. Now, if a1 and a2 are the periods in the x and y direction, so if you consider the period here is a1 and this is a2, so the shortest distance here will be a1 and a2, so they are the lattice vectors, right. So, you can say that eta xy satisfies the translational symmetry relation given by this. So, what is that? Eta x plus m1 a1 comma y plus m2 a2 will be same as eta xy. So, that is how you can also understand that for all integer values of m1 and m2, this relation will be satisfied. So, this is a periodic 2D lattice. This periodic function is represented as a two-dimensional Fourier series in the form of this one. So, any periodic function can be expressed as a Fourier series that you have learnt. So, eta xy can be written as all these different components here. Okay. You can write summation L1 starting from minus infinity to infinity, L2 starting from minus infinity to infinity, eta L1 L2, okay, and then you can have exponential minus j L1 G1x exponential minus j L2 G2x. Now, what are this G1 and G2? We have seen in the previous lecture. G1 is basically 2 pi by a1 and G2 is 2 pi by a2. These are the fundamental spatial frequency along x and y direction. What will be the unit? Radian per mm. Okay. And L1 G1 and L2 G2 are nothing but their harmonics, because any frequency, spatial frequency is fundamental frequency. If you multiply them with integers, you will get their harmonics, right. So, the coefficients that you have seen eta L1 L2 depend on the actual profile of the periodic function, that is the size or the shape of the rods. So, let us look into the 2D Fourier transform of the periodic function. So, is composed of points on a rectilinear lattice as shown in B. So, this is the real lattice, which is basically the lattice points are shown here. Okay. So, we have considered a rectangular lattice. So, this lattice vector is A1, this is A2, but when you convert it into the reciprocal lattice, that is in the Fourier domain, okay, you went to the, from space you have gone to momentum space. Okay. So, here you will call it kx and ky, okay, and this lattice vectors are now 2 pi by a1. So, it is g1, okay, and g2, okay, they can be, yeah, g1 is 2 pi by a1, g2 is 2 pi by a2. There I think there is a typo here, okay, that can be corrected. So, this should have been g1 and this is g2. So, this is how you get the reciprocal lattice. Fine. Now, once you understood that how you get the reciprocal lattice, what are the optical modes of the medium with such symmetry, that you have to find out. Okay. And there will be another important thing, that what is this particular region that we have marked here. Okay. Now, if you consider the waves traveling in the direction parallel to the xy plane, the modes of the two-dimensional block waves are given by uxy, which can be written as pkx ky xy exponential minus j kxx exponential minus j kyy, where this is basically the periodic function with the same period as the medium. Now if you consider this particular reciprocal lattice, the shaded region, the yellow shaded region here is basically the Brillouin zone. So how do you get Brillouin zone? We will come to that, but first of all you have to remember that the wave that is shown here is basically having a pair of block wave numbers. It has got kx and ky, right. So another wave with block wave numbers like kx plus g1 and ky plus g2, okay, that will not be a new mode, rather they will kind of they will be same. As shown in the figure, a complete set of modes in the Fourier plane has block wave numbers located at points in the rectangle defined by this one. So what is this one? So kx is defined as minus g1 by 2 to g1 by plus g1 by 2, and ky will be defined as minus g2, so this is 2, okay, minus g2 by 2 to plus g2 by 2, and this particular rectangle is called the first Brillouin zone. And why we are interested here? So if you are able to calculate all the modes in this particular zone, we know it for the entire lattice. So other symmetries may be used to reduce the set of independent block mode wave vectors within the Brillouin zone. So we will come to that concept, which is also known as how to find out the irreducible Brillouin zone. So when all the symmetries are included, the result in an area called irreducible, the result is an area called irreducible Brillouin zone. Okay, so we will take an example here, that in this particular case you can understand that this is basically a square, okay, kind of shape. So here what you can have, you know, you can actually look for rotational symmetry, okay, and mirror symmetry. So from that you can identify that this rectangle, this square or rectangle is better, is a generic term because g1 and g2 are not same. So let us take, say, this rectangle. If you take a mirror, you get this one, and then you put a mirror here, the whole thing is formed, right. So this is the basic Brillouin zone, okay. You can start with it and create the whole thing. However, taking only half of it, because it is also having a rotational symmetry. So if you take half of it and rotate it by 48 degree, you will get the other half, okay. So that way this becomes the irreducible Brillouin zone, and there are ways of marking it. So you can actually mark this as gamma mx. So what is m? M is the corner point, x is the midpoint of the edge, right. Now a two-dimensional periodic structure comprising parallel cylindrical holes are considered here. So here one important thing, as you can see, they are not actually aligned in a rectangular or square lattice. So if you connect all the center points of these cylindrical holes, so how do you make these holes? First of all, you take this structure and then drill holes in this particular pattern. So if you mark all the center points of this particular holes, you will see this is the lattice, okay. So and from this lattice, this is the direct lattice. So you can see this is A1, this is A2, both are equal, and this angle is around 120 degrees. So this is a hexagonal lattice, right. And or you can also call this as triangular lattice, there is another name for it, okay. So from this you can always convert it to the reciprocal lattice space and find out what is g1 and g2, okay. And in this reciprocal lattice space you can identify the Brillouin zone. How do you do the Brillouin zone? Once again, you take the one center point and then you connect it to all other points like this, okay. So you can draw these lines and then you draw perpendicular bisector, like this. So, you will get this particular one. For this one you draw another perpendicular bisector, you get this one. For this you draw another perpendicular bisector, you get this one. Then you get this one for this line. For this one you get this line. For this one you get this line, and that is it. And then you paint this area with yellow, and you can just show that this is your reciprocal lattice having this brilliance zone. Okay. So, this is the first brilliance zone. Okay. And from this you can also identify, as I mentioned, you can use those rotational symmetry and mirror symmetry and all those things. So, you can identify what is the irreducible brilliance zone. Here you will see that you can identify only this triangle to carry all the information about the brilliance zone. Okay. So, that is how irreducible brilliance zone helps you to reduce the computation and but still give you the same amount of information of a brilliance zone. Okay. So, this we have already covered. So, this is in the shape of a hexagon, right. Now, I think we have already discussed this. For a given lattice with a set of lattice vectors R, how can we determine all the reciprocal lattice vectors G? So, here we are naming the real lattice vectors as capital R and the reciprocal lattice vectors as capital G, and let us find out that what is the relationship between this G and R. Okay. So, we need to find all G such that if you do G dot R, means if you multiply this, okay, this is some integer multiple of 2 pi for every value of R. Okay. So, how do you do that? We know that every lattice vector R can be written in terms of its primitive lattice vector, which are basically primitive lattice vectors are nothing but the shortest vectors pointing from one lattice point to another lattice point. Okay. So, for example, if you take a simple cubic lattice with spacing say small a, the vectors capital R can be written in the form of LAX plus MAY plus NAZ. So, as you can see, it is a cubic lattice, so all the distances are basically same a, and L, M, N, these are basically integer. Now, in general we call the primitive lattice vectors, there are names A1, A2 and A3, right, and they need not be of unit length. That is understood only in certain cases they will be equal to each other, okay, or 2 may be equal, 1 will be different, or so on. And we have already mentioned that the reciprocal lattice vectors, which are denoted by G, form a lattice of their own. Okay, so there is a real lattice and there is a reciprocal lattice. Now, in fact, the reciprocal lattice has a set of primitive vectors Bi. So, there it is Ai, or you can say A1, A2, A3. Here it will be B1, B2, B3. So, it means every reciprocal lattice vector G can also be written as G equals L B1 plus M B2 plus N B3 and so on, where L, M, N are basically integers, right. So, our requirement that G dot R is 2 pi N boils down to the requirement that this particular product that you have seen, okay, just to not to confuse that this L, M and N should be equal, you can actually mark them as L prime, M prime and N prime, okay, that these integer values are basically different to these integer values, but this multiplication should give you 2 pi N. Now, for all the choices of L, M, N that you have seen, okay, there should be some value of N that holds that equation correct. So, if you put some thought, you will see that only in the case when Ai dot Bj equals 2 pi, this will happen if I and j are equal, and if they are unequal, okay, this will be unequal, there is a typo here, you get 0. Okay. It means compactly you can write that Ai dot Bj, the two unit vectors, when you multiply them, if they are in the same direction, you get this value 1. Okay. If they are in different direction, you get 0. So ai dot bj will give you 2 pi delta ij. Okay, this is how you can write it compactly. Now given the set a1, a2 and a3, our task is to then find out the corresponding set of the reciprocal lattice vectors, that is b1, b2 and b3. And what is the condition? The condition boils down to ai dot bj should be equal to 2 pi delta ij. Now one way to do this is to exploit a feature of the cross product. So you remember this formula that x dot x cross y equals 0, and that is happening for any vector basically. So if you take x y as any vectors, if you do this particular operation, you will get 0. So using that, you can also find out that the primitive reciprocal lattice vectors can be obtained from the real lattice vectors using this formula. So b1, b2, b3 can be obtained from a1, a2 and a3 using this particular relationships. Okay. Now in summary, we can say that when we take the Fourier transform of a function that is periodic on a lattice, we need only include the terms with wave vectors that are reciprocal lattice vectors. Now to construct the reciprocal lattice vectors, we take the primitive lattice vectors and perform the operations that are given in this equation. Simple. Now each direct lattice has a unique reciprocal lattice. So if you have knowledge of one, you have the knowledge of another, because they will correspond to uniquely to each other. So if you take a direct lattice like this, so the blue one shows the reciprocal, the primitive lattice vectors here, and in the green one, the capital ones are showing the primitive reciprocal lattice vectors. So you can actually correlate this. So if the direct lattice is simple cubic, your reciprocal lattice also transfer to be simple cubic. If you have BCC, when you do the reciprocal lattice, you will come up with FCC. If you have FCC, you will come up with BCC, and if you have hexagonal, you will still come up with hexagonal. So this is how they correspond to each other, and this is how you can convert, as I have already shown how to convert the reciprocal lattice vectors. Okay, so capital T1 and capital T2 are basically the reciprocal lattice vectors. Okay, and the blue ones are basically the small t1 and small t2 are the real lattice vectors. So this is how you can actually get the values of each other. So these are the values of how to obtain capital T1, capital T2, capital T3. This is for 3D system, okay, and these are for 2D system. And all the reciprocal lattice vectors must be an integral or integer combination of the primitive reciprocal lattice vector. That means this T, P, Q, R, or it can be called as G, capital G, as you have seen. They will be nothing but capital P or L prime, as you have seen before. Capital T1, that is the this is the primitive reciprocal lattice vector T1, T2 and T3. So they are basically integers, P, Q, T, R. All these are integers. Different books use different notation, just remember these concepts, okay. And the next important thing is to how to define the different planes using Miller indices. Now Miller indices identify repeating planes within the periodic structures like crystals. So if you look into the definition of reciprocal lattice vector, this is how we have defined just now. So P, Q and R, they can be called as the Miller indices of the planes in the direct lattice, which is described by a reciprocal lattice vector PQR. So let's see how it works. So if you have a 1 0 0 plane, that means along x you have 1, and it does 0 0 means it will be parallel to both y and c. 1 1 1 plane means it will cut all three axes at, there is a 1 bar. So 1 bar is -1 along x, okay, and then you have 1 along y and 1 along z. So this is a particular plane that is given as this Miller indices 1 bar 1 1. Okay, you can also have some more, like this is, if you try to write them in terms of the lattice vectors, okay, a1, a2 and a3, you can define them as 1 0 0. This one is, this yellow region one is 0 1 0, this one is 0 0 1, this is 1 1 and then 0, and so on. So this is how Miller indices help you identify repeating planes within periodic structures. Now the last thing that remains here is to see how do you construct Wigner's Sage cell or the Brillouin zone. Okay, we will come to Brillouin zone because the concept that we will see here in Wigner's Sage cell, Wigner's Sage cell happens in real lattices and Brillouin zone happens in reciprocal lattices, but the concept is very similar. Okay, and the construction of this cell is also very similar. So how do you construct it? Let's see. So pick a point in the lattice to build the cell around. So let us pick this particular point, okay, and then for this point construct planes that bisect the region between all adjacent points. Okay, so from this point to this point, this is the connecting line. So you actually put a plane that bisects that region. Similarly, for this to this, you put another plane that bisects this region, and so on. So when you add up all this, you will get this kind of a region, unit cell region, that is enclosed by all these planes. Okay, so this is how the construction is done, as you can see. So from the center point to this point, if you take midway, you first take the connecting line, midway you draw a plane. So you basically get this kind of a section here. Then you have this plane, this plane. When all these planes add up, they will give you this particular shape. Okay. So whatever you have done for Wigner's Sage cell, if you do the same thing in a reciprocal lattice, you will basically get a Brillouin zone. Okay. So the construction of Brillouin zone is exactly similar as the Wigner's Sage cell, just you have to do the same operation in reciprocal lattice. Now Brillouin zone is closely related to wave vectors and diffraction. So analysis of periodic structures is often performed in reciprocal lattice. So that is how, you know, that the study of Brillouin zone becomes very important. Okay, the reason is the Brillouin zone is closely related to the wave vectors and diffraction. So if you take the Brillouin zone of a FCC structure, that is basically a truncated octahedron like this of 14 sides. Okay, not slides, it's 14 sides. So this is basically the most symmetrical Brillouin zone because it is almost spherical. So you can say that FCC lattice is having the highest, you know, symmetry among all the Bravais lattice. So if you try to see the degree of symmetry for different type of crystal and other structures, you will see triclinic has got the lowest symmetry, whereas diamond, which is having FCC structure, it has got the highest symmetry. Okay, and if you go for pseudo periodic like this, they have even further increase in symmetry. Now these are the points of symmetry in a Brillouin zone. So this is, I am showing this in a 3D crystal. So if you think of a planar one, so if you take a cubic crystal, and if you, then the important points are gamma, m, r and x. So these are the points of the irreducible Brillouin zone. So this particular volume will contain all the information of your Brillouin zone. Okay, you do not need to compute it for the entire region, you can only compute it for this one. Similarly, if you take hexagonal, then these points gamma, k, m, l, h and a. So each of these points are defined here, something like, just read out one or two, that m is basically the center of the rectangular face. So this is the rectangular face, this is the center. There is another face here. What is this face? This is a hexagonal shaped face. Okay, so what is L? L is basically the middle of the edge that is joining the hexagonal shape face and the rectangular shape face. So, this point is L. Okay. What is H? H is basically the corner point. K is basically the midpoint of the edge that is joining two rectangular faces. Okay, that is K, as you can see here. So, these are the different irreducible brilliance zones, okay, which are very important for finding photonic band structure as well. And if you take this simple shape cubic one, and if you think only 2D, so you will only have gamma, m and x. So, if you take a cross section like this, that will make this structure a 2D. So, you can only have gamma, m and x. Here also you can think of this is a hexagonal one, but if you take a 2D, so you can get a 2D hexagonal lattice or a triangular lattice, you can say. So, there you have gamma, k, m and gamma. So, only this part will be in the 2D one, right. So, that is the whole idea of having irreducible brilliance zone, as I mentioned, that if this is your lattice and this is your unit cell, okay. So, your objective would be to only find out the region that this region should replicate the entire one. So, if you take only this particular region, as we have discussed before, if you take a flipped version of it here or rotate it here, you can get this particular square, and then you can use mirror on the other side to get this left one. So, once you have the upper half, you can put a mirror here and you can get the entire structure. So, it means if you only compute for this triangular region, it will contain the same kind of information. Okay. Similarly, in FCC lattice, we have seen this is the brilliance zone, which has got 14, it is an octahedral shape with 14 sides. In between, if you actually identify this region, which is the smallest volume of space within the brilliance zone, that completely characterizes the periodic structure, is called the irreducible brilliance zone. So, you cannot further reduce your brilliance zone. So, this is the minimum portion of the brilliance zone that is required to give you the overall property of the brilliance zone, okay, and that is why it is called irreducible brilliance zone. And so, two things here. So, this octahedral shape is the full brilliance zone. This painted region here, this volume is the irreducible brilliance zone, and this will help us in reducing the computational burden, okay, for finding out different modes and the photonic band structure for this particular crystal or crystal setup. Okay. So, with that we will stop here today, and in case you have any doubt, you can write me to this email address mentioning MOOC on the subject line. Thank you.